Namaste and welcome to this lecture on mathematical foundations for machine learning. We started off with ideas of probability. We will be continuing with probability for some more time, as I said. So, we saw the definitions of sample space, a random experiment, then we looked at event, then we looked at the parallels between set theory and probability theory and so on. We are just getting on with our journey into probability. So, what we are going to do is we are just going to recap some more ideas of set theory which would be useful in defining some terms in our probability language. We will look at all that and then we will get on with the ideas of axioms of probability and interpretations and so on, right. So, let us get on with our definition. So, recall. In set theory we have the set theoretic operations, namely union, intersection and so on. So, what we are going to do is complement and so on. So, we are just going to recall these ideas of union, intersection and complement, and then we are going to make a few more definitions which are relevant to our probability theory, right. So, we are going to look at union, union of sets, right. So, suppose I have we did this in the last lecture, we have this, suppose I have the sample the universal set S and then I have this subset A and then I have another subset, let me say I have this subset B. Now, what we are going to say is we are going to say union of the set. So, we are going to denote that by the symbol U. So, I am going to say A union B is nothing but union of the set A and B, and we are going to say that it is the set of all elements it is the set of all elements in that are either in A, that are either in A or B or both, A or B or both, and that is what we had shown in the last lecture as this. We said that this entire thing is basically my A union B, right. This is how we defined it. Of course, leave the portions which are out of the shading which has come out of those circles that I have put. So, forget about that, whatever inside A and B, that we have we call that as the union. The symbol is basically this, right. Okay. And the second thing that we want to look at is basically intersection. Intersection of set. The notation is this, everybody knows. So, I have this, I have my Venn diagram here where I have A and I have set B. So, let me write this, this is set B, this is set A. Intersection is basically just this guy, the fellow who is common to both. That means, we are going to make this definition now. We are going to say A intersection B is basically the set of all elements contained in both A and B. Right, and then we have our intersection complement. So, I am going to look at the third operation, which is complement of a set. Complement of, let us say, set A. So, what do we mean by that? I have again my universal set, I have this set A. Complement of A is nothing but the set of all those fellows which are in the universal set, but not in the A. So, this entire thing other than A, right. So, this is basically the complement right. So, this is basically the complement. So, how are we going to define this? We are going to say that this is set of all elements in S that are not in A. This is what we call as complement. Now, from here I am going to make two more important definitions. What is that? I am going to make one first definition that I am going to look at is mutually exclusive or mutually disjoint. We are going to say mutually exclusive. We will get back to this definition in the parlance of probability soon, but we will just look at this mutually exclusive events. So, what we are going to say is collection of set, a collection of sets, let us say A1, A2 etc. AN is mutually exclusive if AI intersection AJ is empty set for I not equal to j. That means they do not have anything in common. This is something which we have equivalently we have studied something in our idea of vector spaces. We said that okay, somewhere the dot product is being 0, we said that they are orthogonal. Of course, I am not trying to bring that notion here, but I am just saying that this notations whatever that we see is like something similar to what we have done there. So, what we are going to say is we are going to say that AI intersection AJ is empty set for I not equal to j, and you call that as your mutually exclusive set, or you can also call them as mutually disjoint set, mutually exclusive or mutually disjoint. Right. These are also called as mutually disjoint sets. The next definition that we have is something very again interesting. We are going to call this as collectively exhaustive collection. Collectively exhaustive. Collectively exhaustive, what we are going to say is a set or a collection of set. Collection of sets, let us say A1, A2 etc. AN is called collectively exhaustive if and only if the union of these fellows A1 to AN results in my sample my universal set or the sample space, right. So, we are going to say this if and only if A1 union A2 union etc. union AN is equal to my sample set S, my universal set S. Is that okay? So, a collection of set A1 A2 AN is called collectively exhaustive if and only if A1 union A2 union AN is basically my universal set itself, right. So, what we are going to do is we are going to we just put this in a compact form. We say that union I is equal to 1 to n a I is equal to the sample space. This is collectively exhaustive. We can do the same thing for mutually exclusive also. Mutually exclusive, you just say between pairs. So, you just say that a I intersection a j is the empty set. So, this is what we have as mutually exclusive, and here we have our collectively exhaustive. Now, what I am going to do is I am going to put these two together. I am going to look at a collection of set which is both mutually exclusive and collectively exhaustive, right. I am going to look at a collection of set which is both mutually exclusive and collectively exhaustive. So, okay, a collection of mutually exhaustive sets, mutually exclusive sets, mutually exclusive and collectively exhaustive and collectively exhaustive set, right. You have a collection A1, A2, AN where pairwise they are mutually exclusive, that means A I intersection A j is empty set, and the union of all these collections is going to give me the universal set. We have a name for it and you call that as a partition. This you call it as partition, right. That is a collection of set which is both mutually exclusive and collectively exhaustive is called as a partition. So, how does that look like? You take this, I have this sample space or universal set S. I am sorry, I have been interchangeably using sample space and universal set, but the moment I start discussing probability I will use sample space. Now that I am doing the idea of set, I would call this as the universal set. So, I am going to have A1, A2, A3, A4, A5. So, let me take this as A1, A2, A3, A4, A5. Now, if you look at this, no two events have or no two subsets have anything in common. That means A I, in this case if you see A I intersection A j is empty set for I not equal to j, and you see this union of I is equal to 1 to 5 union of A I gives me the universal set S. So, this is called as a partition. This definition of partition is very important because when we do the idea of Bayes theorem we will actually use this definition of partition there, right. Okay. Okay. So, now we have all these things. So, the next question that we ask is, look, I have all these things, fine. So, where do I get into the notion of probability? How do I define probability? What is probability? We are getting into that definition of probability now. Okay. So, I hope you understood the ideas of partition, collectively exhaustive, mutually exclusive and so on, and partition so on. So, now what we are going to do is we are going to look at the notion of probability, right. So, what is probability? How are we going to define that? Let us do that. Okay. So, how do we define probability in the first place? Our high school definition of probability tells us that, okay, fine, you suppose I want to look at what is the probability of getting ahead, you do this relative frequency definition where you say that, look, count the number of heads in the total number of trials that you have done. So, the ratio of number of heads to the total number of trials that you have done is going to give me the probability of or the relative frequency of getting the head. So, that is basically how we are going to define our probability also, but then we will do a bit of what would you call, we will do a very formal definition of this probability a bit later. Right now what we will take is total number of the number of favorable outcomes to the total number of outcomes. That is basically your probability definition. So, what we are going to do is we are going to take this right now. So, I am going to do this. Consider tossing a coin n times, right. Consider tossing a coin n times. Now, what we want to do is in the n times that you toss a coin, I want to find out what is the number of times that I have got a head, right. So, let us assume this. So, I want to look at the number of times head occurs in the n trials. Right. Now, what I am going to do is I am going to look at the relative frequency definition of probability, where I will use this relative frequency of, let us say, tail in n trials of, let us say, the head is nothing but the number of times we had head, number of times head occurred in n trials divided by n. You can say that, okay, limiting case, you can say that limit n tending to infinity, the number of times you had the head by n, that is going to give me a probability number. So, this number is going to be, I am going to say relative frequency, I am going to say 0 less than or equal to relative frequency. I will just use in n trials of a particular event A is going to be less than or equal to 1, where A is, let us say, event A. In our case, this event A was basically getting head. So, this is what we have, right. Okay. So, what we want to do is you can actually take this to be your probability number as n tends to infinity. So, your probability of event A is nothing but limit n tending to infinity, number of times event A occurs by n divided by n. That is basically the probability of event A. Now, what we have is we need to build on this definition. There is a small problem with this definition. The problem is, you will see that suppose I take an interval a comma b, there is a small problem with that. So, suppose I take this interval a comma b, let us say both a and b inclusive. I want to look at the probability of get the, okay, let us take a to be 0 and b to be 1. So, I want to look at the interval 0 comma 1, and I want to look at the probability of getting, let us say, p of 0.5. The probability of getting this number 0.5. Now, if you go by this definition that is given up there, there is only one time that you have 0.5 to occur on the number line. Any other number is going to be 0.5, 0, 0, 0, 1 and so on, exactly 0.5, it occurs only one time, and the number of points within this interval 0 comma 1, it is basically infinity, and it is not just a I mean, you can say infinity and leave it, because you take the number of points between 0 and 0.1, you have infinitely many number of points, and 0 and 0.001 there are infinitely many points, 0 and 0.01 there are infinitely many points. So, you basically get into this uncountably infinite fellow, and therefore, this definition of probability of event A would not work in this case, where you say okay, the probability is basically the number of times A occurs by n. It is going to be a complicated case in that case, in that scenario. So, in which case when we encounter this scenario, we basically talk about something else, which we will see when we do random variables, we will talk about that. Right now we will keep this definition as limit n tending to infinity number of times A occurs divided by n, right, countably infinite n, that is what we are going to look at here. Okay, let us go ahead. So, what we have is we want to look at some kind of what we call, we want to look at this axioms of probability. There are 3 important probability axioms. So, we have axioms of probability. So, what are they? The first one is basically, therefore, okay. Let us also look at, before getting into this axioms of probability, let us look at something a small subtle and very important idea about probability, and then we will go ahead. So, what did we say here? We say that in the previous case we said this probability of event A, that means I am going to call this as P of A, is basically limit n tending to infinity, the number of times this event A occurs divided by n, this is what we have, right. Therefore, this notation that we see here P of A, this is something which we normally encounter in any mathematical domain, where we say f of x, which is basically some kind of a function, right. So, therefore, what I am going to do is I am going to say look, this guy, this P of A is basically a function which is going to map the sample space to real number, okay, such that, so we have this. So, what are we going to do is we are going to have this definition. We say that we will also come to this one more tricky term which is here, we will understand that a bit later, we will come to that. So, what we are going to say is we say that a probability measure, a probability measure P of something, right, P of something is a function, that maps events in the sample space, that maps events in the sample space to real numbers right, events in the sample space to real numbers. What we are going to do is such that okay, we will put this, then we will come back to this to the sample space to real numbers in the interval 0, 1. In the interval 0, 1, right. So, basically what we have is we have a function P which will basically take those events which are defined on the sample space, and to each of those events that you have defined on the sample space, it is going to allot, or it is going to map a real number in the interval 0, 1, and that is what we call as our probability measure, right, that is what we call as probability measured. So, we are going to say that P of A, the probability of the event A is nothing but, let me put this is P A, this is basically a number in the interval 0, 1, 0 and 1 inclusive, right. Okay. Now, what we want to do is we want to look at this idea of axioms of probability. We want to look at the axioms of probability. So, what are there are 3 basic axioms which you would have studied in your high school. We will just recap those axioms here. So, you have the first axiom which says number 1, for any event A, P of A is greater than or equal to 0. That means, the probability of event A is a non-negative number. It can never be a negative number, it is always non-negative. The second property or the second axiom is basically saying the probability of the sample space is always 1, and the third one we are going to say that for mutually exclusive events, mutually exclusive or disjoint, mutually disjoint events, let us say A1, A2 etcetera A n, P of A1 union A2 union etcetera union A n is equal to P of A1 plus P of A2 plus etcetera P of A n. Now, we can write this as probability in short we can write this as probability of union I is equal to 1 to n A I is nothing but sigma I is equal to 1 to n P of A I. This is also something which you would have studied. That means, you have a mutually exclusive event. So, you add up all these fellows and they take the union of all these guys, the probability adds up there. So, the probability of the union is nothing but the sum of probabilities if the events are disjoint. So, this is what we have, right. Okay. So, let us just make a couple of comments here and then we will go ahead. In fact, we have the definition of probability space and so on, which I am not getting it into it right now, but we will just make some interpretations of these whatever that we have written and then we will go ahead with our definitions and further topics in probability. So, what are we going to do? So, the first one, axiom 1, what is the meaning of axiom 1? We said that if A is any event, any event, we said P of A is greater than or equal to 0. This is basically the non-negativity of probability measure. Right. So, what it says is this and we should also understand that maximum probability is basically corresponding to the probability of the sample space. Therefore, the other interpretation that we have is the probability of any event is basically bounded between 0 and 1. So, what we are going to do is I am going to write this. So, we are going to say this 0 less than or equal to P of A less than or equal to 1. The maximum being the sample space probability. So, then the second axiom. So, in fact, either you do this or you can always say the 0 less than or equal to P of A. Some of the textbooks say P of A is greater than or equal to 0, some of textbooks say 0 less than or equal to P of A less than or equal to 1. So, I mean these are the axioms of probability that you have. So, I can take this, it is always there in the interval 0 comma 1. The second axiom interprets to the following axiom 2. What does it say? It says the probability of the sample space is 1, right. It says that the probability of sample space is 1. That means there are two things that here that we need to note. One is sample space itself is an event, because we remember we said that event is nothing but the subset of the sample space, which is basically to which we associate a number between 0 and 1 and call that the probability. Now we have said P of the sample space is 1, that means the sample space itself is an event, and we know that every set is a subset of itself. So that also kind of puts this definition P of omega is equal to 1, but what it actually means is the following. It says that it basically says this in randomly performing a trial. So okay, we say that in performing a random trial, the outcomes must come from the sample space only, right. The outcomes cannot come from anything else, the outcomes have to be from the sample space. Therefore, what we say is in performing a random trial, the occurrence of one of the sample space elements, the occurrence of one of the sample space elements is always 1. Now do not confuse this with saying, suppose I have a sample space which had this sample space which is like 1 2 3. Now do not say that P of 3 is 1, no, P of 3 may be 1 if I define my probability of 1 and probability of 2 to be 0 or very small, but what it says is probability of omega is equal to 1, probability of the sample space is 1. That means the outcomes that you have can only come from this sample space, and therefore whatever outcome that you get out of this sample space says that the event of that sample space has occurred, and therefore that probability must be equal to 1. That is the interpretation that we are giving here, right. So what does it say? It says that there are 3 elements 1 2 3, and whenever any of these elements occur, that means whenever one of these numbers come as the outcome of the experiment, it simply means that the sample space event has occurred, and therefore since the sample space, the event can occur only from the sample space, we always say that the sample space probability is always 1. That is the interpretation that we have. Okay. Okay, so the third interpretation is what I have already given. It says that okay, if you have mutually disjoint events, the probability of their union is nothing but the sum of their probability. So this is something which we have already had. So the question is now, what are the consequences of this axiom? So let us look at that. What are the consequences of the axioms, or these three, there are certain properties which you can derive or which follow directly from the axioms that you have defined. So let us look at this. So the probability P of whatever that measure, the probability measure P of that you have, we say that it satisfies the following, The first one, what it says is the probability of the empty set, which is equal to this, is equal to 0, right. This is equal to 0. This can be very easily obtained. You can say that the sample space union the empty set is basically the sample space itself. Now what we have is probability the sample space and the empty set are basically mutually disjoint fellows. Therefore, I can write this as P of omega union empty set is equal to P of omega. Now, this I can write it as, since they are disjoint, I can write this as P of omega plus P of empty set is equal to P of omega. Now, what do we get? These two gets knocked off. So, we get P of sample empty set is equal to 0, right. There is also a name for this empty set that we have, because we are talking in terms of events. Since we say that probability of empty set is 0, that means empty set must be an event, and therefore, and this is an event which can never occur. What does this mean? Suppose if I toss a coin, I must get head or a tail. No outcome is definitely not an outcome at all, because empty set contains nothing. Therefore, no outcome is not an outcome at all. Therefore, what we say is the probability of the empty set is 0, implying that the empty set can never occur, and therefore, we give a special status for this empty set, we call that as the impossible event. So, we are going to define this, we are going to say that, look, I have this empty set, we call this as an impossible event. Right. What are we going to say? We are going to say that the probability of an impossible event is 0. Right, that means probability of empty set is 0, right. The second consequence, or the second what do you call the property that you can note is this. Remember, we had the definition of, let us say, A complement, which was nothing but the set of all elements in the sample space, but not in the set A. Therefore, A and A complement form a partition. Therefore, A union A complement is basically, note that for any set A, A union A complement is basically the sample space, right, or the universal set. A union A complement is the universal set. So, what I am going to do is, and we know that A and A complement form a partition, they are mutually exclusive. That means if A occurs, A complement cannot occur, and A union A complement, we see that it is the universal set itself. Therefore, A and A complement form a partition of S. Therefore, what we have? We have P of A union A complement. I am going to talk about this P of A union A complement, which is nothing but P of omega, the sample space. Since A union A complement, therefore, I will write this A intersection A complement is empty set. So, I am going to have this as P of A plus P of A complement is equal to P of omega, which implies P of A complement is equal to 1 minus P of A, because P of omega is 1. Now, that tells us something again. It is not that probability of A complement is 1 minus P of A, it also means that if A is an event, A complement is also an event, right. What does this mean? This simply implies if A is an event, A complement is also an event. Right. This is one more, and the third consequence that we have is the following. We are going to say, for any two events A comma B, any two events A comma B of the sample space omega, P of A union B is nothing but the probability of A plus probability of B minus the probability of their intersection. Because we have done double counting, I want to remove one of those counts. I will write this as P of A plus P of B minus P of A intersection B, and the last one is this: if A is a subset of B, right. If A is a subset of B, this notation is subset, right. If A is a subset of B, then the probability of A is less than or equal to probability of B, right. This is yet another important what do you call consequence that you find, right. Okay, good. Now, is that all? Like, are we done with this? No, there are few more things where we are going to talk about the idea of mutually disjoint events, mutually disjoint events. So, what does this mean? That means if you have mutually disjoint events, A intersection B is empty set. Therefore, I am going to say P of A union B is equal to P of A plus P of B, right. This is there. Now, the most important stuff here is this mutually exclusive or mutually disjoint events. It says that these two events cannot occur together. So, that is the interpretation that we want to look at. So, what we are going to say is we are going to say that two events are mutually exclusive implies exclusive implies P of A intersection B is equal to the probability of the empty set, which is equal to 0. What does that mean? This simply implies the two events A and B cannot occur together right, they cannot occur together. Now, what does that mean? It simply means that, okay, suppose A is the event of somebody dead and B is the event of somebody being alive. It says that, look, A and B, somebody cannot be dead and alive at the same time. That means these two events cannot occur together. That is what this means, right. These two events cannot occur together simultaneously. That is the most important takeaway for us as far as the definition of mutually disjoint events is concerned, because this interpretation of mutually disjoint events helps us go further. That means we are going to ask this question, say I have two events here A and B, which says that they cannot occur together. That means if A occurs, B definitely has not occurred. If B has occurred, A has definitely not occurred. Therefore, what is it that we can gain from occurrence of this event A or event B about the other event? So, that is more important. That is the kind of update that we are looking at, and that is more important, and that is something which we will see in the next class, and we will build up on this kind of an interpretation to look at some more pairs of events, and then we will go ahead with our Bayes theorem. So, the focus of the next class will be recapping this idea of mutually exclusive events, its interpretation, followed by certain questions that we want to ask, and then again we will try to interpret, and then we will move on to the idea of conditional probability, and then we will move on with the idea of Bayes' theorem and so on. So, in the next class we will look at the idea of mutually exclusive events and its interpretation. Namaste.